Can you hear me?
Hear you okay.
Is that okay? Okay, thanks. Yeah, do give me a shout if something is not working properly. Also, feel free to interrupt for any questions, of course. This is joint work with Pierre Abulker, Unjung Kim, Nilo Dewi Sintiari, Nicolas Trotignon, and Frederick Harvard. So the motivation for our study is, well, even whole free graphs, they've been studied for a while now. They naturally arise in the context of perfect graphs, the study of perfect graphs, where we now have the strong perfect graph theorem characterizing perfect graphs by no odd holds, no odd anti-holds. So yeah, even whole free graphs came up in that context. And our hope was, if we have a better understanding of the structure of even whole free graphs, we might also get or be able to work towards efficient algorithms for, yeah, there are several open problems still on even whole free graphs. So for example, coloring is still open, whether this can be done in p-time, and the maximum independent set problem, so the stable set problem. And another motivation, which actually was my first incentive to look at even whole free graphs, was the question whether even whole freeness can be tested in the bounded degree model of property testing, which is a sort of very, very efficient approximate recognition. And I might, yeah, speak a little bit about that towards the end as well. So, yeah, this is the content. There's an introduction. I'll spend probably large parts really of the talk speaking about even whole free graphs, excluding a minor, and then a little bit, depending on time, about testability of even whole freeness. So for us in this talk, all graphs are simple and undirected and finite. No self-loops, no multiple edges. All graph classes are closed under isomorphism, and we sometimes call a graph class a property. And a class of graphs has bounded degree if there is one universal constant, d, such that all graphs in the class have degree at most d, meaning that the max degree of their vertices is at most d. And then we have some special graphs like a complete graph on n vertices, that's denoted by kn. So n vertices and all possible edges present, and Cn denotes the cycle of length n. And we will also encounter some grids and walls. So there I'm just defining them by picture. This is a 5 by 5 grid. So 5 rows, 5 columns. So there, yeah, we'll encounter n by n grids. This is a triangulated n by n grid or triangulated 5 by 5 grid. Looks like this. And then we have, we'll be speaking about walls. This thing here is an elementary 5 by 5 wall. Again, you can see 5 rows. And then there are also sort of 5 columns or 5 vertical paths. And I've highlighted 3 of them here. This one isn't highlighted, but there's another one and another one here. So they're a bit wobbly, but there are some vertical paths as well. 5 of them. Okay, and then so this is an elementary wall, and then we say a graph is a wall if it is obtained from an elementary wall by potentially subdividing some of these edges multiple times. So yeah, any subdivision of an elementary wall is a wall. And we'll also encounter subgraphs, contractions, and minors. So take a graph and find graphs in that big graph. So for graphs G and H is an induced subgraph of G if H can be obtained from G by a sequence of vertex deletions. H is a subgraph of G if H can be obtained from G by a sequence of vertex deletions and or edge deletions. And H is a contraction of G if H can be obtained from G by a sequence of only edge contractions. and H is a minor of G if H is a contraction of a subgraph of G. Okay, so different, 4 different operations there. And we will say that a graph G is H-free if G does not contain H as induced subgraph. So H-free will always mean H induced subgraph free. Yes, tree width is also in the title. So here's the intuition of tree width. I'm assuming many of you will have encountered it, but I'm giving the definition briefly to remind everybody. So the intuition is tree width measures how close a graph is to being a tree. So graph G has tree width at most k if G can be pieced together from subgraphs of size at most k plus 1 in a tree-like fashion. So there's a graph here, and there are some subgraphs, and you can sort of see how it's pieced together. And these subgraphs have at most 4 vertices, so this graph has tree width at most 3. It happens to have tree width exactly 3 because you can't do any better. And this is the formal definition. The tree decomposition of a graph G consists of a tree and a family B, so T is a tree. B is a family of subsets of vertices of G, also called the bags, such that 3 properties hold. First one says every vertex of G is covered in some bag. Well, every vertex is covered, so for every vertex it's contained in some bag. Second one is every edge is covered. Every edge of the graph is contained in some bag of the decomposition. And the third one is the connectivity condition. So a vertex of G can occur in multiple bags, but if it does so, these multiple, the nodes of these bags containing that vertex need to be connected in the tree. And then the width of the tree decomposition is the max size of its bags minus 1. And the tree width of G is then min-max, so it's the minimum width taken over all possible tree decompositions of G. And yeah, this was first introduced by Robertson and Seymour in the famous graph minor project, but it's also independently discovered under a different name in a more algorithmic context as well, actually. So it's a very robust notion. And yeah, we say that a class of graphs, we're speaking about classes of graphs. So a class C of graphs has bounded tree width if there exists one universal upper bound again. So exists the number T such that all members of the class have tree width at most T. And if C doesn't have bounded tree width, we say it has unbounded tree width. And some classical examples, trees have tree width at most 1. So class of all trees, bounded tree width, bounded by 1. Complete graphs, the complete graph on n vertices has tree width n minus 1. Basically, it doesn't have tree shape at all, so we have to put everything in one bag. So complete graphs have unbounded tree width. Class of all complete graphs, unbounded tree width. The n by n grid has tree width n. So again, class of all grids has unbounded tree width. And similarly, the class of all walls has unbounded tree width. And if H is a subgraph of G, then the tree width of H can be at most the tree width of G. And similarly with induced subgraphs, contractions, and minors that we saw before. So tree width cannot increase under any of these operations. And yeah, what's the algorithmic use of tree width? Why is tree width so useful? Well, many problems that are NP-hard in general become tractable on bounded tree width. And there is one very famous theorem that summarizes this quite nicely, which is by Bruno Courcelle in 1990, saying that if you have a class C of graphs of bounded tree width, then every graph property that you can express in monadic second order logic with counting is decidable in linear running time on C. And that includes many problems, some problems that are NP-hard in general and others as well. So you can express the stable set problem, clique, vertex cover, dominating set. You can express the existence or non-existence of a fixed subgraph, induced subgraphs, planarity, bounded genus, excluded minor, connectivity, colorability, Hamiltonicity, having an even number of vertices, that's where the counting comes in, and being a perfect graph, and being an even whole free graph. Okay, so even whole free graphs, that's the other part in the title. Let's introduce those. So yeah, let C be a cycle in a graph, and we say that an edge of the graph is a chord in C if the endpoints of that edge are vertices of C that are not adjacent on C. That's sort of a crossing edge. And a hole in a graph is a chordless cycle of length at least 4. And a hole can be even or odd according to the parity of its length. And we say that a graph is even hole free if it does not contain an even hole. So examples include complete graphs. They don't contain any holes. Trees, similar. Chordal graphs, which are defined as hole free graphs. So they're all even hole free. And then here are some perhaps relevant graphs that are not even hole free. So graphs that do contain even holes. So this is a template here. It's not one graph. It's denoting a whole family of graphs, which look like this. They have 3 edges. So the solid lines are edges. The dotted lines are paths of length at least 1. And any graph that fits this template contains an even hole. These are called thetas because they have the shape of a Greek letter theta. So, okay, why do they contain an even hole? Because notice we have these 3 paths here, 1, 2, 3, from left to right. And if you look at their lengths, there must be 2 of them who have the same parity, whose lengths have the same parity. So maybe even, and together they will form an even hole. Okay, and this one is similar. It's another pattern. So these solid lines are just edges in the graph. So 2 triangles like this, and then there are 3 paths of length at least 1, the dotted lines, connecting the triangles like this. And again, you can see for parity reasons, 2 of these paths must have the same parity, and so you will find an even hole. Okay, so we immediately see, because complete graphs are even hole free graphs have unbounded tree width. Oh yeah, this is the other even hole free graph. I wanted to show you one that is less trivial than chordal graphs and cliques and trees. So here's one. There's a big clique here, but then these vertices are connected to that long path in a intricate way as well. So interesting even hole free graphs exist. Okay, so yeah, so one natural question to ask is which subclasses of even whole free graphs have bounded tree width? Again, in view of we can do lots of stuff efficiently on bounded tree width. And so it's known from 2010 that planar even whole free graphs have bounded tree width. So that's by Silva and Linhares Sales. And then for more recently, by a result by Cameron, Da Silva, Huang, and Vuskovic, tells us that if you're even hole free and you also don't contain a triangle, then you have bounded tree width. So even hole triangle free. And a natural question to ask after this is, do even hole free graphs of bounded clique number have bounded tree width? And indeed it was asked by Cameron, Chaplik, and Huang paper. So, right, bounded clique number. So when about with a bound on the maximum size of the cliques that occur. And it turns out this is not the case. And there's a construction by Sintiari and Trotignon where they show an even hole K4 free graph, or a class of even hole K4 free graphs that has unbounded tree width. So already K4 is this, K3 cannot be replaced by K4. So if you look to this construction, you will find it uses unbounded degree. So that class has unbounded degree. And also it contains complete graphs as minors. So arbitrarily large complete graphs as minors. No bounds on the degree, no bound on the kn minors. And we asked ourselves, are these two necessary? Right? Are these necessary for constructing graphs of unbounded tree width? Or conversely, if we bound the degree, do we get bounded tree width? If we bound the maximum size of the clique-minors, do we get bounded tree width? And here's the part about minors. So we proved together with Pierre and Onjung and Dewey and Nicolas, we showed that even whole free graphs excluding a minor have bounded tree width. Actually, we show something slightly more general. We show that the class of all theta prism-free graphs, excluding a minor, have bounded tree width. Right, so it's sufficient not to contain any of these thetas or prisms that we saw earlier. And this implies the result by Silva and Linhares Sales that planar even whole free graphs have bounded tree width because planar graphs can be characterized by forbidding K5, for example, K5 and K3, but they are minor. They exclude a minor. Okay, and for the proof, we establish a sort of induced grid theorem for graphs excluding a minor. So for a graph class excluding a fixed minor, we prove a kind of grid theorem, which I will speak about a bit more in a bit. Let me speak about the other part, the bounded degree. So what we do is in the paper we have a conjecture saying that even whole free graphs of bounded degree have bounded tree width. And we proved the restricted versions of it. So if we have a degree bound of 3, we prove it's true. Also subcubic even whole free graphs have bounded tree width. And we do this via a structure theorem for subcubic, actually theta prism free graphs. So this again, the slightly more general graph class here. And also we look at, so this is degree 3. If we go up to degree 4, we forbid pyramids as well. So even whole pyramid free graphs of degree at most 4 have bounded tree width. And this is proved slightly differently, combining structural results, known results, with some new results to show that these types of graphs cannot contain any K6 minor. And then we plug in the previous theorem where we just get for free that the tree width has to be bounded. Okay, so pyramids, these are pyramids. Again, they are graphs, they're a family of graphs that fit a certain template, which is this one here, where you have 3 vertices like this, solid edges, solid lines are edges, triangle like this, and then the dotted ones, the dotted lines are again paths of length at least 1. Okay, and this also, this also has some implications in property testing in the bounded degree model. So namely, from this first one here, it follows that subcubic, for graphs of bounded degree 3, even whole freeness is testable in the bounded degree model. But I will speak a bit more just on this slide, because now, in the meantime, the conjecture in full generality has been proven by Abrishami, Chudnovsky, and Vushkovich. They proved that even whole free graphs of bounded degree have bounded tree width. And this, together with a theorem with Frederick Harbert from a while ago, implies that even whole freeness is testable in the bounded degree model of property testing with constant query complexity and sublinear running time. Okay, so this is sort of the setting out the picture. I'll speak a bit more about even whole free graphs excluding a minor and how we get the bound on the tree width, because I think it's nice, and it's what we do there is maybe fits into the talk, I'm hoping. And so let me speak a bit more about that. So I'm just repeating it here. Even whole free graphs excluding a minor have bounded tree width. So excluding a minor just means there must be at least one non-trivial graph, one non-empty graph that is excluded as a minor in the class. Okay, so there's some more terminology here. So the line graph of a graph G is the graph LG, whose vertex set is exactly the edge set of the original graph G. And two vertices in the line graph are adjacent if their corresponding edges in the original graph share a vertex. And a graph G is called chordless if no cycle in G has a chord. And we call the line graph of a chordless K by K wall a K by K co-wall. So to remind you, this is a picture here of a K by K wall. So something that looks like it has this brick structure plus some potential subdivisions. And this is the line graph of a chordless K by K wall, not of this one, but of some. Excuse me. So you get little triangles here where those degree vertices are in the wall, right, from the line graph. And the fact that there's this little word chordless here basically means that for the co-walls, you will have maximum degree 3. You will not get any vertices of degree 4. Okay, so here's the induced wall theorem for graphs excluding a minor that we use on the way for our proof. It says the following. So given a graph H, there exists a function f such that for every H minor free graph G and K, well, either the tree width of G is bounded by a function of K for f of K, or G contains a K by K wall or a K by K co-wall as induced subgraph. Either small tree width or one of these two. Okay. Let's first argue why the theorem follows once we have this excluded wall theorem. Okay, so this is the theorem again. So let's look at this. We have this twofold scenario. We exclude a minor, so there is some H that that is excluded. So we have the twofold scenario. Either we have bounded tree width, which is what we want anyway, so we're happy, or we have the other case, and let's just argue that we can't have arbitrarily large walls or co-walls here in our class, and that's not so hard to see. If you have a wall like this, you can find a theta by taking this vertex up here and down here, and then you have 3 paths connecting those vertices as in the template for a theta, which means we find an even hole, right? So already a little wall, 3 by 3 wall like this cannot occur. And similarly, if we look at this is a 3 by 3, or we can see in the 3 by 3 co-wall that we find a prism with a little triangle here, a little triangle here, and then the 3 paths connecting those triangles like this. So already we cannot have 3 by 3 co-walls. Okay, so this second case basically then can't occur, so we have bounded tree width. Does that make sense? Okay, so so really it's sufficient now to prove this theorem here. Now there is one famous theorem, maybe the first one of this flavor, again by Robertson and Seymour, which says that there's a function f such that for every graph G and every K, either G has tree width at most f of K, or it contains a K by K wall as subgraph. So note here that we don't require any excluded minors or anything. So that's in full generality. But here we have subgraph and not induced subgraph. Okay. So and subgraph cannot be replaced by induced subgraph, because if you take complete graphs, for example, they have underbounded tree width, so then we're not in this case. We have to be down here in that case. But complete graphs don't contain walls or co-walls as induced subgraphs. The only induced subgraphs they contain is other, complete graphs, basically. We can just delete vertices for induced subgraphs. So we don't use this one, but we use another theorem that's actually which is this one here, by Fomin, Golovac, and Tilikos, which says, so for every graph H, there's a function f such that for every connected H minor free graph, G and K, the tree width of G is bounded by f of K, or G contains a so-called gamma K or pi K as a contraction. So recall, contraction is something that is obtained merely by contracting some edges. Okay, and a pi K is again defined by picture. Gamma K and pi K is defined by picture. So this is gamma 6. It's a triangulated 6 by 6 grid, plus this vertex here is universal to everybody on the boundary, so connected to everybody in the boundary. That's a gamma 6. And a pi 6 is gamma 6 plus 1 universal vertex, right? Which we cannot just remove because we're looking at contractions and we can't delete vertices. So one of these we get. So let's think about this a bit more. So this gamma 6 being a contraction means that every little vertex here, every little circle here, is actually obtained in the big graph by contracting some vertices. So it corresponds to a connected set of vertices in the original graph that were then contracted into that little vertex. Okay, and different vertices here correspond to disjoint, so pairwise disjoint connected sets in the original graph. And also there'll be an edge between the two vertices in the contraction. Well, if and only if there was at least one edge between the two connected sets in the original graph. And so for two vertices here that do not have an edge, it means nothing goes across between the two connected sets in the original graph, which it will be useful for us. Okay, so we use this, and here's a sketch of the proof. So we're starting with a graph G that excludes some fixed graph, H as a minor. We assume G is connected, which is without loss of generality, because we could treat connected components. And we assume K is very large, okay? So large enough to make the proof work. And we also assume the tree width of G is larger than f of K, because if it's not, we're good. And then we know by the previous theorem that G has to contain gamma K or pi K as a contraction. Okay. Now, if it contains a pi K, remember with that additional universal vertex, we just delete the universal vertex to obtain a gamma K. So we can just work in gamma K. Deleting is fine for us because we are after induced subgraphs. Right, and we say that a fork is a tree, so a graph that is a tree with exactly 3 leaves, and a semi-fork is a graph obtained from a triangle by appending little disjoint paths of length at least 1 at each vertex of the triangle. So it's basically like a fork, but there's a little triangle in the middle. And what we do is we look at a constant size part of the gamma K. So we forget what is going on in the boundary. We just take a constant size part somewhere in the interior, So constant size, this is 4 by 4. It looks like a triangulated grid. And we use this to find, well, either an induced fork or an induced semi-fork in the original graph. Okay, because we recall that each of these vertices corresponds to a connected set in the original graph G. So what we do here is we pick 3 sets like this, like A prime, B prime, and C prime, and we pick a vertex A and A prime, vertex B and B prime, vertex C and C prime. And okay, let's first connect B and C by a shortest path that goes through this set here called big B and S, and here capital C prime. So since these sets are connected and there are edges here in the triangulated grid, there exists a path, so we pick a shortest path, like this. Okay, this is called P in the picture. And then what we do is from that vertex A, we take a shortest path through this blob here and this blob here to connect to P, like this. Shortest path from that little vertex to any vertex on P. And then you need to, there's a bit of a case distinction here. So take the last vertex on that shortest path here, call it W, and then look how it connects to P. This can either be a little triangle. So W can have 2 vertices, 2 neighbors on P that are also neighbors on the path. So U and V could be neighbors. And then we get a little triangle here, which will give us a semi-fork, or something like this doesn't exist. So no 2 neighbors of W on P are neighbors on the path. And then we can take W as the center here and take sort of the outermost neighbors on the path, and then we get a fork. We find an induced fork. Right? So the point is really here, once we have a constant size part of gamma k, we can find a fork or a semi-fork. So because k is really big, we pick k to be very, very large. We can find lots of these in a huge gamma k. Each of these here is a 4 by 4 part of the gamma k. And in each of them, we find something that is now either a fork or a semi-fork. We don't know, right? But we find a configuration here. And in this part, we find one as well. In this part, we find one as well, and so on and so forth. So we have 6 of these forks or semi-forks. And then we start connecting them into something that looks like a brick, where we add some paths like this and like this to connect these to form a brick, where you can see that these will be connections to the outside, and this will enable us to produce lots of bricks next to each other and also on top of each other, so to build something that looks a bit like a wall. Okay, and these are induced, right? Because these are far away. There are no edges from any blob here to any blob here, right? So this is induced. That's the nice thing here. Okay, so we get something. So by putting these bricks together, we get something that looks like almost looks like a wall, but it's a bit untidy because these little things here can be, well, forks or semi-forks, and what we are after is to have either a wall or a co-wall. So we would like all of them to be forks or all of them to be semi-forks. But now we get an untidy mix, which we call a stone wall. Okay. So this we need to tidy up, which we do in the next step. Okay. So here's how to tidy it up. This is the lemma summarizing what we're doing. So we're saying for every integer r, there exists an integer n. such that every n by n stone wall, remember that untidy mix, contains an r by r wall or an r by r co-wall as induced subgraph. And for the proof, we use a variation of Ramsey's theorem, which works for bipartite graphs, which is from a paper by Beinecke and Schwenk in 1975. So this says that for every r, there is an integer n of r, such that any two-edge coloring of the complete bipartite graph KNN contains a monochromatic KRR. Right? Remember complete bipartite graph KNN, so n vertices on one side, n on the other side, and edges are all the possible edges going from left to right. Okay, and then we have a two-edge coloring, so every edge is either red or green. And this tells us that or we can find monochromatic complete bipartite subgraphs in there. Okay, so this is the tidying up lemma. So we want to find stone wall, n by n stone wall, which is untidy, and we want to make sure we find either an r by r wall or an r by r co-wall. Okay, so n is very big, but an r is a bit smaller, but it'll grow with n. And we find this as induced subgraph, of course. That's what we need. Okay, so we're given an n by n stone wall, and we define a wall, so to call it W, we define a wall what W prime by contracting each triangle of W into a vertex. So all these little centers of the semi-forks are contracted into a vertex. And we will color the resulting vertex red. And then all the other degree 3 vertices that come from forks, not semi-forks, of W prime, we color green. So yeah, so red is just to remind us this is a center of the semi-fork, and green is this is the center of a fork. And then we define a complete bipartite graph H with vertex set consisting of, well, two sets A and B, where A is a set of all horizontal paths of W, and B is the set of all vertical paths in W. Okay, here's the picture again. The walls have a bit wobbly vertical paths, but these are the vertical paths. Now, here it's important to note that each vertical path has two colored, red or green, vertices in common with each horizontal path. So let's look at the central vertical path here, and maybe the central horizontal path. There are two vertices here that'll be red or green. So they meet on two of them, okay? Not just one like in normal grids. This causes a little bit more work, but this is how we deal with this. What we do is we've got that bipartite graph H, complete bipartite graph H, and we color it with three colors. So if P is a horizontal path and Q is a vertical path, if their intersection contains two green vertices, we color the edge from P to Q green. If their intersection contains two red vertices, we color their edge red. If their intersection contains a mix of both, green and red, we color the edge black. Okay, so we don't have a two-color ring, we have a three-color ring, but we can group two of them together into one color, right, and apply Beinecke and Schwenk's theorem, and this will tell us that H contains a large monochromatic complete bipartite subgraph, H prime. So that'll be monochromatic. That means it'll, right, entirely green or entirely red or entirely black. So in the first case, if it's entirely green, we know that we found some set of horizontal paths and vertical paths that meet in green vertices only. So only in forks, which means that we can easily extract a large wall. Okay, we don't have any triangles at intersections. In case 2, all the intersections between vertical and horizontal will be little triangles, so are red, right? So we can easily extract a large co-wall in that case. And the only case where there's still some work to be done is the third case, where at each intersection we have both a red and a green vertex. But we gained something here. Right? In the third case, we have a mix of both. We gained the fact that both colors, red and green, appear everywhere locally. And with this, it is not so hard to come up with a little bit of rerouting, just changing the path slightly locally, to make sure we also find a large wall. So we can avoid these little triangles and make sure we just move around forks. Okay, and that also gives us a large wall, which is great, which is what we wanted. So, so we find a large wall or a large co-wall, which is exactly what we were hoping for, and this concludes the proof of the theorem. Okay. Okay. Yes. Are there any questions for this? Maybe this is a good point. Or if it's easier to take questions later, I'm not so sure with the setup. Yeah, so let me chat a little bit about my original motivation for looking into even whole freeness and bounded degree. That comes from, well, looking at efficiency when the data set is huge. So in the context when the data set is huge, it's so big that even reading the whole input just once is too expensive. And it's sort of the classical big data scenario that we encounter these days. And yeah, and sort of classical complexity theory where you have, NP hard versus polynomial time as intractable versus tractable doesn't really work very well anymore, because polynomial time, I mean, even just reading everything once, even linear time, can be too expensive. So we need sort of new approaches there. And this, if you remember Courcell's theorem from the start, saying that every property expressible in monadic second-order logic with counting is decidable in linear running time on classes of bounded tree width. Together with, this was with Frederick Harvard, we asked ourselves, can we be faster than this? Obviously, we will have to sacrifice some accuracy, because if we want to be faster than linear running time, we cannot read the whole input even once, so we may overlook things. But yeah, but can we be faster? And okay, so and this is where property testing comes in, which looks at, sort of aims at highly efficient sublinear algorithms. So let me chat a bit about this. So this is a picture of classical decision problems where you're given a property or a class of graphs, right? And you get as an input a graph, and your goal is to decide whether the graph has the property or it doesn't. So whether it's in or out. And in property testing, this picture is slightly relaxed. So we have a property, and then we have sort of the class of those graphs that are epsilon close to having the property, and then there's everything that is epsilon far. And what we aim at here is for an input, for input graph G, we want to distinguish two cases. We want to be able to distinguish the case of G having the property from the case of G being epsilon far from having the property with high probability. So probability at least 2/3. Okay. If the input graph happens to be fall into this this part here, so epsilon close to the property but not in, we don't care what the algorithm answers. Okay. We want to accept when we have the property, we want to reject when we're far, but here we don't care. Okay. And the aim is to do this very fast, or to be very efficient. So yes, so this is so different models of property testing have been introduced over the time, and here we're interested in the bounded degree model, which is first introduced by Goldreich and Ron in 2002, and this assumes that all graphs have a uniform upper bound on the degree. Okay, so we need to say what it means to be close or to be far. This wasn't clear from the picture I showed you just now. So this is how it's defined in the bounded degree model. So graphs G and H, both on the same number n of vertices, are called epsilon close if we can make them isomorphic by modifying up to epsilon times dn edges of G or H, where modifying means inserting or deleting. And this is an epsilon fraction, small fraction of the potential total number of edges that such a graph could have when you have a degree bound of D and n vertices. Okay. So we're allowing a small fraction of this to be modified. And then if G and H are not epsilon close, then they're called epsilon far. And G is epsilon close to a class if it's epsilon close to some member of that class. And otherwise, it's epsilon far. And then, if we want to run algorithms for property testing, we cannot read the whole input. That'll take linear time. So we need a different type of access to the input. So what type of information do the algorithms get? They get the number n of vertices of G, and then they have oracle access to G, which means they can query. They can say, okay, for vertex V, vertex number 17, give me its one neighborhood. And this is assumed to be possible in constant time. So getting answers to these queries. And we measure the running time in the usual way, running time with respect to n, the size of the number of vertices. And then a very important complexity measure here is also the query complexity, which is being perhaps even more studied than the running time in this context, which is the number of oracle queries depending on n. And really, the typical aim is perhaps to go for a constant query complexity. Also, sublinear has been considered, but constant query complexity. And here are some examples of what is known. So on bounded degree graphs, so in this model, the following properties are testable with constant query complexity and constant running time. So connectivity, edge connectivity, vertex connectivity as well, being Eulerian, excluding a fixed subgraph, excluding a fixed induced subgraph. And then there are also results of showing that certain properties are not testable with constant query complexity, like bipartiteness, or being a sort of expander graph. So these are the very early results from the first paper by Goldreich and Ron as well, and many other things have been obtained in the meantime. For example, Hamiltonicity is not testable with constant query complexity, and many others. And with Frederick, what we did, we proved that in the bounded degree model, when we also assume bounded tree width, so two things, bounded degree and bounded tree width, then we can show that every property that is definable in CMSO is uniformly testable with constant query complexity and polylogarithmic running time. The constant number of queries and polylogarithmic running time. So indeed, sublinear running time, which was sort of what we were hoping for. Although, remember, Courcell's theorem does not require a degree bound, but the degree bound here comes in because it just comes with the model. Okay. And now, even-hole freeness can be expressed in the CMSO, and also k-bounded tree width is testable. And combining these two, we get this corollary that I showed you earlier by Abrishami, Studnovsky, and Vushkovich, who proved our full conjecture. Even-hole freeness is testable in the bounded degree model of property testing with constant query complexity and polylogarithmic running time. because what they proved is even whole freeness of bounded degree have bounded tree width, so we get the bounded tree width here for free once we have bounded degree, and then we can just plug this in. Okay. So yeah, this concludes my talk. So I talked about even whole free graphs including a minor, excluding a minor have bounded tree width. We proved this via an induced grid theorem for minor free graphs. Yeah, we proved some results on subcubic even whole free graphs, show that they have bounded tree width, slightly more general graph classes really here. This is via decomposition theorem. Then even whole pyramid free graphs of degree at most 4 have bounded tree width. We spoke a little bit about implications in property testing also of now the full conjecture being proven. And we still have one conjecture remaining, which basically asks whether we can have an induced grid theorem for bounded degree graphs. And yes, that is it from me. Thank you very much for your attention. Thank you.
Thank you, Isolde, very much for your talk. Are there any questions? If there are any questions, please just go ahead. Okay, Martin.
Thank you. Thank you for this nice talk, Isolde. I have a question related to this. There are two basic results for even whole free graphs, and some of them more generally, that either bounded degree or excluding a minor implies bounded tree width, right? Are these two properties known to be independent? So bounded degree and excluding a minor in the case of even whole free graphs? Or does one imply the other?
That is a good question. I would think they're independent. Now you want to know why? So, okay, the question is, if I have bounded degree on even whole free graphs, does that imply that I exclude a minor? Or could that imply that I exclude a minor?
Or the other way around?
Yes, yes. Bounded degree on even whole free graphs. Right. So if I have bounded degree, I cannot have large clique-minors, of course. Oh, I can have large clique. Oh, yeah, I can in general, yes.
Well, wait a minute. If the degree is bounded, then the true width is bounded, right? But then you cannot have large clique-minors.
Yeah, but that's using that the tree width is bounded. Yes.
Yeah, of course, but it's true.
Yes, then it's true. Yes.
Maybe the converse, or the converse could perhaps still fail, right? Or
so if you have bounded degree width, bounded, you exclude a minor, then you have bounded tree width, but you may still have large degree. Yes. Well, trees, just trees.
okay, yes.
Yeah.
This is easy.
So yeah, I was thinking whether you were asking whether once you have one of these results, the other one follows. But yeah, but
okay. So apparently, the one implication still holds. But of course, it's easy to see once you have the result. But otherwise, maybe not so easy to see. Thank you.
Okay.
Okay. Any other questions, remarks? Well, if not, then let me just know that Isolde will be with us for another couple of minutes. So if there are any other questions regarding the talk, you could discuss with her after the official seminar is over. So Isolde, thank you once again very much, and see you all of you next week.
Right, thank you everyone.
Bye.
Bye, guys.
Just to say, it was a really nice talk. Thank you.
Glad you like it.
Yeah. Full of good results, and I have plenty of notes, and I had questions, but you answered them during the talk somehow. So.
Okay, yeah. It always feels a bit weird to be talking to just a screen somehow, and I'm happy I can see you now and chat a bit.
Would it be possible to get a copy of your slides? I forgot to ask before, but that would be nice.
Yes, sure. I'll email you. Yeah.
Thank you.
Yeah.
I especially like this Ramsey theorem application. This is really beautiful.
Yes, it turns out not to be very difficult once it's there.
Did you have to merge the colors, or you could just apply a variant for many colors?
To be honest, I didn't really look for any variants. Are there variants for multiple colors for bipartite graphs?
I don't know, but you merged the colors to apply the one for two colors then.
Yes, I didn't think more. Yeah, I mean, one could. What would be nice to do is to see what the actual function is. We don't know this, right? If one wanted to optimize this and try and make it as small as possible, then it would probably make sense to look into good variations of that. But yeah, we haven't done that. Yeah, also, I'm cheating a bit. In the paper, we actually even use 4 colors just to make, then we get 2 rerouting cases, and just to make rerouting a bit easier. But that increases the function even more. So it's a trade-off between the rerouting and the number of colors. But both ways can be done.
So this is probably the first kind of induced theorem, right, for large walls?
To my knowledge, yes.
I'm sure it will find many applications.
Well, yes, although, I mean, assuming H-minor freeness is quite a strong assumption already, right? But I'm curious. I'm hoping. Of course, I mean, the theorem that we use by Filikos and Fomin and